Hello AP Chemistry students. Today we'll be talking about the second FRQ question on the 2018 AP Chemistry exam. Before we get started with that, I want to take a look at this reaction right here. Here we have the reaction of dinitrogen tetroxide into nitrogen dioxide, and then the opposite over here. These are complete reactions as all of the reactants are used up and all of the products are created. But when they're happening concurrently, it's known as a reversible reaction. This reversible reaction is especially important as N2O4 is a rocket propellant. So this is one of the equations that helped get man to the moon. At a certain time, reversible reactions reach a state known as dynamic equilibrium, which is seen right here. This means that the forward and reverse rate of reaction are equal. So there's a constant amount of products and reactants at any given time. Let's get started with the first part of the question. So the first section gives you this equation up here and then asks you to draw the reactant mixture. Because of conservation of mass, we should have 8 nitrogen atoms on this side and 12 oxygen atoms on this side, because you just count up which ones are dark, which ones are light, and they should be the same over here. If we look up here at the equation, for every 2 NO2 that are made, you need 2 NO and 1 O2. There are 4 NO2s when you count them up on this product side, so we need 4 NOs and 2 O2s. Let's draw those. Okay, now that we've drawn those in, we have enough to create all of the NO2s on this side, but we're still missing 4 oxygen atoms and 4 nitrogen atoms. So let's just add 4 more NO to complete this question. Okay, moving right along, this next question asks for the equilibrium constant at 298 Kelvin. So we're going to use this equation and we're going to plug in Gibbs free energy, which is given to us right here. It's in kilojoules per mole, but we're going to multiply that 1,000 by 1,000 to make joules per mole. So it's going to be e to the negative 180 joules per mole divided by R, which is our gas constant that's given to us on the reference sheet, and then also divided by our temperature, which is going to be 298. That's given right there in the question. And then our Gibbs free energy has the lowest number of sig figs with 2. So in our calculator, we're going to get 0.70 yada yada, and we round that off to 0.70 for sig figs. So K equals 0.70, and that's enough for that question. This next question is a theoretical question. So it asks, if the vessel starts at 1 atm, will the pressure of N2O3 be 1 atm at equilibrium? So clearly no, but we have to justify why. Well, if the K is 0.7, which we found in the last question, and K is products divided by reactants, that means that there's some amount of reactants present in equilibrium. Therefore, the pressure of the products cannot be 1 atmosphere because the reaction does not go to completion. So therefore, the answer is no, and you could say the justification is because the reaction is not a complete reaction. Okay, another theoretical question. This question asks if increasing the temperature will increase N2O3. Why or why not? So the answer is no, because if you can see here, delta H is negative. So the reaction is exothermic, meaning that heat is added on the product side. Therefore, if we increase the temperature, we're going to increase the rate of this reaction, making more reactants, not more products. So the answer is no, because the reaction is exothermic. Okay, so this next question asks us to create a Lewis dot diagram for this molecule. So I'm going to put a single bond between each of them and then fill in all the octets besides hydrogen. Now let's look at our formal charge. Remember, formal charge is the group that the element's in minus how many electrons it has around it. So we look at hydrogen, it's in 1, has 1 electron, 0, perfect. Oxygen, 6, has 6 around it, 0, perfect. But this nitrogen and this oxygen cause us a little trouble. This nitrogen is in 5, but it has 6, so it's 5 minus 6 is a charge of -1. And same thing with this oxygen, it's 6 minus 7. 6 minus 7 is -1. So these two have a formal charge of -1. We want them all to be 0. So we have to turn this bond into a double bond and then take away this electron pair and this electron pair. Now it's 5 minus 5 is 0, and 6 minus 6 is 0, and this is going to be your answer for this question. Okay, so the final question asks for the hybridization of nitrogen in this HNO2 molecule. So nitrogen has 1, 2, 3 charge clouds around it. Remember, a charge cloud can be a lone pair of electrons, it can be a single bond, triple bond, double bond. So there are 3 charge clouds around the nitrogen. For 2 charge clouds, it's an sp. For 3 charge clouds, it's an sp2. And then for 4 charge clouds, it's an sp3. So it falls under this category, therefore it's an sp2 orbital. So in this FRQ, we graphically represented dynamic equilibrium. In this question, we calculated K using delta G, and then we answered some conceptual questions about dynamic equilibrium, which was made easier by understanding dynamic equilibrium, rates of reaction, and of course, the difference between complete and reversible reactions. This concept is obviously important because this could be the reaction that gets a man to Mars in a real-world application. So I hope you enjoyed. Thank you so much for watching.